This conference will now be recorded.
Good afternoon, students. So unfortunately, class was suddenly given to me. Okay. So in this class, we are going to discuss about how we can derive that EMF equation of single phase transformer. So before that, I will explain what is the working principle of transformer and what are the parameters are involving in operation. So let's move on to the topic. Students, can you see this video? Please reply in voice. Are you able to see this video?
Yes, sir.
All right. So working principle of single phase transformer. So I'm going to draw that circuit diagram for transformer here. So this entire part we call as core, and the material made up of core is silicon steel or cast iron. So this is the material we are using for construction of core, and the construction is in the form of laminated construction. So what is the purpose of laminated construction here? To reduce the eddy current losses. Okay, now, so this is the purpose of laminated construction. Now I'm going to draw the primary winding and it is secondary winding, right? So here it is a primary, the entire circuit we call as primary circuit and the entire circuit we call as secondary circuit. Now when we are applying the voltage on the primary, we can call as V1, that is primary voltage. Due to this voltage, the current will be flow through this winding. Already you guys know that when a current is flow through the winding, the flux will be generated, right? And this flux will be traveling from here to here, that is from primary to secondary. So we can call as maximum flux. So that's why primary winding and secondary winding both are connected in magnetically and isolated in electrical. Now when the flux is touches this conductor, so that winding, here also the current carried by this secondary circuit, that is I2. Now finally we were applying the load across the load is V2. So now what are the parameters are involving in this working principle means primary voltage, that is V1, secondary voltage, that is V2, primary current I1, secondary current I2, flux, maximum flux, and N1 and N2. So these are the main parameters are involving in the working of transformer. Now our intention is we need to find that whether the transformer is step up or step down. So step up or step down means if it is step up transformer, then V1 is less than V2. So step up means primary is low voltage and secondary is high voltage. So it means that the V1 is less than V2. Now if it is step down transformer, V1 is greater than V2. So this is the relation we can say in terms of voltage. Now in the terms of number of turns we can write N1 less than N2, N1 greater than N2. Now we need to find that induced EMF in the transformer. So the EMF induced here we can denote it as E1. The EMF induced here we can denote it as E2. Now our aim is we have to derive this induced EMF E1 and E2. So that was given by that EMF equation of single phase transformer. Now let me see this. So here let me see some of the parameters involving in this EMF equation. One is flux, that is flux in Weber, and what is the frequency of AC supply? So tell me answering in voice. So because I can't able to see the chart. What is the frequency of AC supply? Students, what is the frequency of AC supply? What is the value?
50 hertz, sir.
Right. So the value of frequency is 50 Hz, and N1 is number of primary turns, and N2 is number of secondary turns, and V1 is supply that is input voltage, that is primary voltage, and V2 is secondary voltage. E1 is induced EMF in the primary winding, and E2 is induced EMF in the secondary winding. Now these are the parameters are involving in the EMF equation. Now we are going to derive that how we can obtain the EMF equation of single phase transformer. So that formula was given by the average, the average rate of change of flux is given by d pi by dt, right? So how we can obtain means this is the sinusoidal waveform for the flux available in the transformer. This is the waveform, and at this point we are getting that maximum flux pi m, and if you taking this half cycle, the time period is t by 2. If you take this one, you can write t by 4, right? Now you can write that the d pi, instead of d pi you can write pi, and dt, how we can write, what is the time taken for maximum flux? T by 4. So actually we can write in the form of frequency pi divided by 1 divided by 4f. Why? Because the time is inversely proportional to the frequency. So instead of t, I can write 1 by f. So finally we can write 4 f pi. This is the average rate of change of flux. We can write 4 into 5 f into pi. This is equation number 1. Now here already you guys know that AC components. So in network analysis you guys have studied, that is peak value, average value, RMS value, form factor. So now here we are going to discuss about form factor. Why? Because the form factor will give that sinusoidal relation between them, this one. Okay, now let me see that the form factor is given by RMS value divided by average value. So this is the formula for form factor. So why we are going to discussing this form factor means any sinusoidal parameter, that is if any parameter which is involving in the form of sinusoidal, we are going to deals with RMS value, average value, and form factor. So here our waveform in the form of sinusoidal waveform, right? That's why I'm talking about form factor. Now what is the general value of form factor? 1.11. This is the standard value for form factor. Now I want to know that RMS value of change of flux equals to 1.11 into average value. So 1.11 into, what is the average value here? 4f5. 4f5. If you multiply this one, 4.44. So let's consider this pi m. That is a maximum flux, right? So this is referent equation number 2. This is the RMS value of change of flux. Now we need to find that RMS value of induced EMF. Is given by E1 equals to RMS value into, so number of turns 1. So what is the RMS value here? 4.44 into F into pi m into N1. This is the final equation of EMF represented by primary winding. So E1 is equals to 4.44 F pi m N1. Represent it is the equation A. Now the same EMF equation we can get from the secondary. E2 equals to 4.44 F pi m N2. This is equation B. So these two equations are represents that EMF equation of a single phase transformer. Now here, how we can write that maximum flux, that is pi m. So pi m, we can write pi m is equals to B suffix m into E. So what is the notation of Bm here? What we call Bm here?
Maximum flux density, sir.
What we call Bm here?
Maximum flux densities.
Right. Maximum flux density and A is area. So why we can write pi m is equals to Bm into A, that is maximum flux density into area means if you take the conductor here, so this is the conductor. Now when the current is flow through this winding, so in this conductor, the flux will be circulate around the conductor, and this flux should be depends on that what is the area of the conductor and what is the flux maximum flux density. So that's why the pi m we can write in the form of Bm into A. So finally we can represent E1 is equals to 4.44 F Bm A N1. Similarly E2 equals to 4.44 F Bm A N2. This is the two equations of EMF of a single phase transformer. Now from this equation we can find that transformation ratio. Let's see the transformation ratio here. So the transform ratio we can represent by K, right? So here how we can write the K means the ratio between that primary and secondary parameters. So let me note down that primary parameters. One is V1, I1, N1 and E1. These are the all represent that primary parameters, that is primary voltage, primary current, primary number of turns and primary induced EMF. And similarly we can represent secondary parameters. V2, I2, N2 and E2. That is secondary voltage, secondary current, secondary number of turns and secondary induced EMF. Now these parameters we need to represent in the form of transformation ratio is given by K is equals to V2 by V1, N2 by N1, E2 by E1 and I1 by I2. This is the representation of transformation ratio. So transformation ratio means suppose if your primary winding is having 230 volts and secondary winding having the voltage 115. So the ratio that is 115 divided by 230, what you will get? 1 by 2, that is 0.5. This is the transformation ratio. Okay, how the primary winding and secondary winding and how the primary voltage and secondary voltage are transformed from 1 to 2, so from single to double or double to single. So this is the transformation ratio. Now if you observe this equation, how the relation between the voltage and current. So I am writing here V2 divided by V1 equals to I1 by I2. So let me tell you, so you can tell me that how the relation between the voltage and current from the relation, whether it is directly proportional or inversely proportional. So tell me by using this relation. What is the relation between the current and voltage? Directly proportional or inversely proportional? This one and this one. So from the relation, you can easily get that the relation between the voltage and current. Voltage is inversely proportional to that current. So it represents that when primary voltage is increases, primary current will be reduced. When primary current decreases, primary current will be increased. So you can say that when the voltage is high, current will be low. Okay now similarly, when secondary voltage is high, secondary current will be low. When secondary voltage is low and current will be more. This is the representation of transformation ratio in the transformer, right? So next we'll see that construction of transformer. So construction, it is the most important question. So in a transformer unit, you may get EMF equation or construction. So these two questions are important, so you can get any question from these two questions. Okay now let me see the construction. So before going to the construction, it is a it is a laminated construction. You have to write that the transformer is a laminated construction, and the laminated construction is used for that to reduce the eddy current losses. So that is the purpose of laminated here. In the point of construction, how many types we have? The point of construction, how many types of transformers we have?
Three types, sir.
Three types. So what are the three types? One is core, shell, and berry type. Now let me discuss one by one in experiment point of view. Okay now suppose if you want to design the core type transformer, the full structure is should be like this, but they are considering the number of plates like this. So they are cutting these plates like this, and finally they are adding. So finally you will get the structure like this. Okay now so they are cutting that core in L shape. Okay now so after these two types of L, they are adding to each other, then you will get the final shape like this. And the material which is using in the construction of transformer, one is cast iron and silicon steel. Now when we can use the cast iron and when we can use the silicon steel means, when the transformer we had to use that more power rating, we can go for cast iron. So for high rating, for small rating we can go silicon steel. Okay now let me see that what is the thickness. So what is the thickness of this plate? We can see the thickness of the plate is 0.35 mm to 0.5 mm. So this is the thickness of this plate. So each plate we have to be bunched together, then we can finally we got that structure like this. Now so this type of structure having the laminated construction, and it is used to reduce that eddy current losses. What is mean by eddy currents? How we can obtain the eddy currents? Do you have any idea about eddy currents? Eddy currents అనేవి ఎలా ఫామ్ అవుతాయి?
Sparks will
What? How we can reduce the eddy, how the formation of eddy currents? Eddy currents ఎలా ఫామ్ అవుతాయి? Right. So no problem, I will tell you that. Suppose if the circuit having the contact like this. So this is the contact switch. Now when the switch is suddenly opened, right, there be a formation of gap between these two terminals, right? This is the gap. Now when the switch is suddenly opened, still there is a flow of current in between the two terminals, these two terminals. Now this current we call as eddy current, and this current makes that sparks happening in this contacts. Okay, now to reduce this type of unwanted currents and currents flowing the air gap, we are using that laminated construction. Okay, now right, so this is about core type transformer, and they are cutting this sheets in the form in the shape of L type. Now let us see the shell type. For shell type transformer, we are getting the final shape of shell is like this. Now how they are connecting means E shape and U shape. So these are the two shapes. They are cutting the plates. After that, they are bunched together. Finally, we will get this shape like this. And here the thickness of the lamination, the thickness of the metal is 0.2 mm to 0.35 mm. This is the thickness of the shell type transformer. Now most probably where low winding is required, that is a primary and secondary. So where the small rating of transformer is required, there we can use cell type transformer. For example, in laboratories we require only 230 volts, right? So it is having the ratio of 115 to 230, that is 1:2 ratio. In this case, in this type of transformers, we are supposed to use the shell type transformer. Why? Because when the size of the transformer is going to be increased, the material also increases. So it is difficult for economical problem. That's why this type of transformer is used where low voltage rating. So that is approximately single phase voltage, that is 230 volts. At that condition, we can use this cell type transformer. Where we go for three phase supply, that is 400 volt, 400 k, 400 volts like that. At that condition, we can use that single that is core type. So for three phase, we are using the three core type. So one is for R phase, second one is for Y phase and B phase. So here we are using three core type transformer, and finally we will get that three phase transformer. And finally we have berry type transformer. So berry type transformer should be like this. So this is the berry type transformer. Here, what is the drawback of this type of transformer means it requires that more material when compared to core and shell. So that's why berry type transformer is not using in real time applications. This is the reason. And one more thing, it requires that more, it occupies the more space. So that much of space we are not providing for that transformer. So that's why it is not using in the real time application. Now, if you observe this diagram here, this blades shape of blades should be called as a core. Okay now, and this internal part, this part is called as low voltage winding, LV winding, and this one we call as this one high voltage winding. So generally, first of all, we need to provide that low voltage winding. After that, we need to provide that high voltage winding, because this is the why we are using this type of construction means if you are providing that high voltage winding at first, it makes that more losses happening in the structure. So that's why first of all we need to provide that low voltage winding, after that insulation, and then high voltage winding. Then only we can reduce that losses. So that's why this type of construction is happening in the transformer. That's why the transformer getting that efficiency is 90 to 95%. Now let me see what are the insulating materials we are using in the transformer. Not only transformer winding, we can use in the generator winding and motor winding. The first one is ignited paper. So ignited paper, it is look like a brown color. Okay now, so brown color, and it is very thick than that normal paper. So what is the importance of ignited paper means if this paper is dipped in that oil, it never be react. So it is still it is a good condition. So that's why ignited paper is using as a insulating material. And next one is mica. So mica also one of the insulating material we are using in the transformer winding and transformer generator motor. And next thing is porcelain paper. Porcelain paper or porcelain paper or porcelain cover. It should be in the form of white. If you observe that in motor winding shop, you can observe the one white paper, right? White, it's like a plastic paper, white. So that is the material we can use for insulating. And the last one is wood. So these are the four major materials we are using for that insulating on the electrical machines. So okay students, this is about today's class. So now we discussed that is construction and EMF equation. In tomorrow class, we are going to discuss about how the transformer will be behaving without load and with load. So that is means అంటే ట్రాన్స్ఫార్మర్ అనేది లోడ్ ఉన్నప్పుడు ఎలా వర్క్ అవుతుంది, లోడ్ లేనప్పుడు ఎలా వర్క్ అవుతుంది. So that is the topic we are going to discuss in tomorrow class. In that, if the transformer is without load means the secondary is open circuited. Okay na? So when the secondary is open circuited, there is no load. At that condition, the copper losses will be zero. Why? Because the copper losses is completely depends on that. Complete depends on the load. If there is no load means there is no copper loss. And so that is the first case. In second case, we are using that, we are operating that value in by using that by using the load. So generally we have the three types of load in the general purpose. What are the three loads means? One is resistive load, inductive load and capacitive load. Already we did that experiments in the machines lab, right, by using the resistive load, that is load test on DC shunt generator. So the resistive load should be like this. And capacitor load and inductive load. So what is the difference between these three types of load means? If you take that resistive load, its power factor is 1. It is unity power factor. Now if you consider that inductive load, the power factor is always less than 1. That's why it has that lagging power factor. And capacity load, so capacity load having the power factor is always more than 1. That's why it is having that leading power factor. Now I will give the example of inductive loads. That is what we are using the devices in our home appliances. These are and all belongs to the inductive load. That's why we are getting that lagging power factor. If it is leading power factor means our current will become 0. సో మనకు అది ఇండక్టివ్ లోడ్ లాగింగ్ పవర్ ఫ్యాక్టర్ ఉంది కాబట్టి మనకు కరెంట్ బిల్ అనేది సర్టెన్ అమౌంట్ వస్తుంది. ఇఫ్ వీఆర్ యూజింగ్ ద కెపాసిటీ లోడ్ మీన్స్ చేస్తే వాళ్ళే మనకు పే చేయాలి, బికాస్ the power factor will be leading. Okay na? So this is the topic we are going to be discuss in tomorrow class. So okay students, this is about today's class. We will discuss in tomorrow remaining topics in tomorrow class. Thank you.